This presentation introduces Layer 3 addressing concepts and routing. In the previous sessions, we have covered Layer 1 hub device and Layer 2 switch. Now it's time to move to Layer 3. The main function of Layer 3 network components is to interconnect local networks. This includes communication between different network types and internet connectivity. The operation logic is based on the Layer 3 header processing. Let's recap the basics of the network layer. This layer is responsible for communication between local networks, and it is achieved by introducing two addresses: network address and host address. The process of data propagation between networks is called routing. Also, I would like to remind you that the Layer 3 PDU is called a packet. In the following slides, we will be talking about the most popular Layer 3 protocol, the IP, or Internet Protocol. It is a part of TCP/IP protocol stack, and there are two main versions in use, version 4 and version 6. Version 6 is more advanced. However, version 4 is still dominating, especially in industrial applications. So let's focus on IPv4. There are some protocol characteristics I would like to highlight. IP is connectionless, which means we don't have to establish a communication session before sending data. It provides us with best effort service with no guarantee of delivery or maintaining packet order. It supports priority and fragmentation and has no error checking mechanism. During the encapsulation process, the IP packet is placed inside of the data field of the Ethernet frame. It is also known as payload. Similarly to PDU of any other layer, IP packet has a header and data parts. You can see IPv4 packet structure on this slide. The header has a lot of fields, including source and destination addresses. This time, those are IP addresses. IP addresses are 32 bits in length. To make it more readable, people split IP addresses into 4 pieces. These pieces are called octets because they have 8-bit length. IPv4 address carries information about both network address and host address. The network part always comes first. According to the classful network concept, the network class defines how many octets are occupied by network address. For class A, the network address part is 1 octet long, and the host part occupies the remaining 3 octets. Class B provides 2 octets for network address. Class C has 3 octets for network address part and only 1 for host. Class D is used for multicast and Class E is reserved for experimental usage. Each class has a defined address range, so you can easily identify the address structure based on its value. This approach was used in the beginning of Internet era, where we had a lot of addresses and few network hosts. Nowadays, classful addressing cannot provide efficient address utilization, so classless addressing is used. In classless addressing, we need additional parameters to define the address structure. That parameter is subnet mask. It clearly defines which part of the address is identifying network address. To get network address from an IP address, we have to perform a binary AND operation with the subnet mask. Binary AND is similar to multiplication, so you can get 1 only in case of multiplying 1 by 1. Other combinations will result 0. Basically, after performing AND with subnet mask, we will zero out all the host bits, and that will be our network ID. Here are examples of subnet masks for different classes. Mask always has high bits set as 1s. Besides decimal notation like 255, 255, 00, network engineers use slash notation, which shows how many high bits are set as 1. Let's have a detailed example. The IP address is 192.168.168.23. Here is the same address written in binary format. Network mask is 255.255.255.0. Let's also convert it into binary. Now you can see why this mask is also named /24. It has 24 high bits set to 1. After performing binary AND operation with this IP address and mask, we will get the network ID 192.168.168.0. Subnetting is a technique when we divide a given network into smaller pieces that are called subnets. It enhances IP address range utilization and improves network manageability. In this example, we have the original network 192.168.3.0/24. It means that we can assign an address to our hosts in the range from 192.168.3.1 to 192.168.3.254. The address 192.168.3.0 cannot be assigned to host because it is a network ID, and the last address 192.168.3.255 is used for broadcast. To perform subnetting, we can borrow more bits from the host part to identify the network ID. Let's borrow one. Subnet mask in this case would be 255.255.255.128 or /25. As a result, we will have two smaller subnets for the same address space. First subnet will have the same network ID as original one, 192.168.3.0, but with /25 subnet mask. It will provide available host addresses from 192.168.3.1 to 192.168.3.126 and a broadcast address 3.127. Second subnet will have 192.168.3.128 network ID and available host addresses from 3.129 to 3.254 and broadcast address 3.255. This table lists subnet masks from /25 to /30. In the subnets column, you can see the number of subnets that you can get from the original /24 network by using that mask. Hosts column means maximum number of hosts available for each subnet. Here is one more subnet calculation example. Original network 192.168.3.0/24 is subnetted using 255.255.255.192 mask. The upper row of the table shows you last octet of the IP address. According to the mask, we are borrowing two more bits for network ID. They are marked with red color on the slide. By altering these 2 bits, we can get 4 different values for network ID: 3.0, 3.64, 3.128, and 3.192. Each subnet will have one network address, one broadcast address, and 62 addresses for hosts. As you see, no matter what size subnet has, the first and the last addresses are always reserved for net ID and broadcast. Now that we know what an IP address is and how to determine network ID, let's take a look how this is used in the communication process. We have two computers on this diagram that are connected via Ethernet switch and thus belong to same subnet. A subnet is a single broadcast domain. Each PC has an IP address and subnet mask set up in network adapter settings. Before PC1 can send something to PC2, It will perform a special check to figure out how it should be done. So first step, it will determine the network ID of the destination host. This is done by taking IP address of the destination, PC2 in our case, subnet mask from system settings, and performing binary AND operation. On a second step, PC1 will compare its own network ID with network ID of PC2. If they match, it means that both computers belong to one subnet, and they are probably connected via one or more layer 2 Ethernet switches. On the computer side, information will be encapsulated and decapsulated going through all 7 OSI layers. As for the switch, it can only read data link layer header and make no changes to the frame. Let's take a closer look at the encapsulation on data link layer. To fill in the layer 2 header, the computer needs to know the destination and source MAC addresses. For the source MAC address is pretty obvious. The computer will just use the MAC of its own network adapter. But how about destination MAC address? In most cases, the computer only knows destination IP address, but not MAC. So we need a special mechanism to get MAC address based on IP. This mechanism is called ARP, or Address Resolution Protocol. According to ARP behavior, the computer will send a special broadcast message which is called an ARP request. The message content is a simple question. Who has this IP address? Please respond. The computer with that particular IP address will respond privately to the requester with its MAC address. Please notice that ARP protocol works only within the same broadcast domain. That is why it's important to keep the rule, one subnet, one broadcast domain. Again, for ARP request, broadcast communication type is used, but for ARP reply, it is a unicast message. This is the ARP packet structure. Notice that it contains both IP and MAC addresses for sender and destination hosts. The operation field can take two values, one for request and two for reply. Now let's go back to our communication model within one subnet. As a first step, our PC1 already compared network ID of PC2 with its own network ID and concluded that they belong to same subnet. Next step would be sending an ARP request to resolve MAC address of PC2. Once PC2 sends back ARP reply, PC1 can continue with encapsulation and send out the frame directly to PC2. To make communication more effective, both PCs will store MAC addresses to IP address correspondence in a special table that is called ARP table. This way, we won't have to repeat same process for every communication transaction. If we want to establish communication between different subnets, we have to use layer 3 devices like routers. You can consider a router like a specialized networking computer which has two or more network interfaces. The main purpose of this device is to route packets from one subnet to another. Routers have their own operating system which can perform this task and also a routing table which is used to make routing decisions. Unlike layer 2 switches, routers do not propagate broadcast traffic. So we can say that each interface belongs to a separate broadcast domain. Every interface of a router has its own IP and MAC addresses. This is how IP packets are delivered across subnets. After network ID comparison, PC1 understands that PC2 belongs to another subnet. If you have ever changed the network settings of your computer, you probably realized that besides an IP address and mask, every operating system has a default gateway setting. All packets with destination addresses of different subnets are forwarded to that gateway. In our case, the gateway should be the router. PC1 will have the IP address of interface 1 as a gateway, while PC2 would have interface 2 as a gateway. This means that from the layer 2 perspective, all communication will be performed as if the destination is the router. PC1 will send ARP requests to check the gateway's MAC address, and then it will encapsulate IP packets and send it to the interface 1 of the router. Then the router will take its turn. It will extract the IP packet from the Ethernet frame, check the destination IP address, and look for the information about destination network in its routing table. For this example, the router should make a routing decision to interface 2, as it is directly connected to subnet of PC2. Interface 2 will use the ARP mechanism to check the MAC address of PC2, then encapsulate the IP packet into a new Ethernet frame, and deliver it to destination. In most cases, there would be multiple routers between sender and destination. Therefore, the gateway will route the packet to the next hop router all the way until the packet reaches the gateway router for the second subnet. Path can vary from packet to packet depending on network status. As a result, you may receive packets out of order. There are several types of routing. Static routing is when network administrator manually defines the contents of the routing table. This is the most simple and predictable way, but as you might guess, it is time-consuming and not friendly to changes. Static routing makes sense for small networks. Another type is dynamic routing. The idea is to use specially designed routing protocols which will allow routers to talk to each other and exchange routing information. MOXA devices support RIP and OSPF routing protocols. RIP is simple, but OSPF is more powerful. The routing table stores information on how to reach the destination subnet. Each routing table entry is called a route. Next hop field contains the IP address of the next router on the way to the destination. In real life, there could be several routes to the same subnet. That is why we need a metric field, which identifies route quality. Routers will use route with lowest metric at first. In case when there is no particular route for the destination network, routers will use default routes which is set to any destination with 0000 address. Routers can run multiple routing protocols and have some static routes at the same time. Thus, you need to remember that static routes have higher priority compared to routes learned by protocols. This final slide is showing you a typical diagram with two subnets. Both subnets are connected to a router which provides cross-subnet communication and access to WAN network. Additionally, the router can perform firewall, NAT, and other advanced functions.